Hello, welcome back to Flipped. Today we are on the chapter of mole concept and stoichiometry. In the previous video, we talked about the different formulas to calculate relative atomic mass, relative isotopic mass, etc. This video focuses on the calculation, and the application of relative atomic mass. So I have two periodic tables in front of me, the A level one and the O level one. You can see here is being labeled as such. So let's take a look at some of the elements in them. In the O level one, calcium has a mass of 40. Do you see it here? This is 40, right? Whereas in the same element of calcium, the mass is 40.1. It's quite interesting, right? What makes the difference? What about other elements like vanadium? It's 50.9 in A level periodic table, whereas in the O level one, it's 51. So what does this tell us? It tells us that O level actually rounds off the decimal place to the nearest whole number to give us a simplified version of a periodic table. And that's why some people call it the fake one, because it's simplified. Whereas the actual one is what we are interested in A level syllabus. So this video actually focuses on how to actually calculate this number. How do I get 40.1? How do I get 50.9, etc. And I'll teach you how to do it. So this is the formula we are so familiar with in the previous video, relative atomic mass, AR, has this formula here, the top portion, let me do a brief recap, the top portion, this is sigma, right, this is what we call a sum of, sum of all the AR, Alright, so this is the first question. Calculate the relative atomic mass of chlorine given its relative abundance of its isotopes. Let me explain this table first. So isotope just means different variations, right? So there are two types of variations of chlorine. One is 35 Cl, one is 37 Cl. 35 Cl has a mass of 35.0 and 37 Cl has a mass of 37.0. Alright, and the abundance for 35 Cl is 75% and the abundance for 37 Cl is 25%. What do I mean by abundance? So imagine I managed to capture 100 chlorine atoms, alright? And 75 of them will be Cl35, whereas the remaining 25 will be 37 Cl. That's what I mean by abundance, is how common for them to exist, how rare it is to exist as well. So you can see that 35 Cl is more common than 37 Cl, 37 Cl is rarer than 35 Cl, hopefully that makes sense. And their abundance, by right, they should add up to 100%, as in this case. So this is out of the way. Let me explain this formula that we are so familiar with, but we have no much use for it. What do I mean? This is the formula to calculate AR, right? Relative atomic mass. The top portion is sigma. We explained it in the previous slide already. The top portion is when you add up everything. Bottom portion is just works out to be 1. Let me do it again. This one just works out to be 1, right? Because 1 over 12 times the mass of one atom of 12C is just 12, and this becomes 1. So it doesn't matter. The bottom will just always be 1. We are only interested in finding out the numerator, the top portion. So how do I actually do this question? It's quite straightforward. I want to find the AR of Cl. This will be actually 35.0, I'm talking about 35 Cl now, times the abundance of 75%, 75 over 100. This is the first part. But since this is a sigma, so I have to add on everybody. And this is 37.0 times 25 over 100. And if you punch in the calculator, you'll get a number of 35.5. And this number, if you check the periodic table, in the actual one, the A level one, you will see that this is the mass of Cl. Why? Because it's the average mass of whatever is being given here, and it's taken into account their abundance. And that's why this formula is so powerful. Because it takes in abundance into account. For example, if my 35 Cl is 99%, my 37 Cl is just 1%. I cannot add them up as such, right? I cannot just take 35 plus 37 divided by 2. That wouldn't make sense, because abundance of 37 Cl is only 1%, for example. So this is the best way, to get a good average, of their different masses. And this will work out to 35.5. This is the second question. Calculate the relative atomic mass of rhenium given that the two isotopes 185 Re and 187 Re and the ratio of 2:3. So this is the same question as previous. Okay, it's just that this one is slightly confusing now, right? In the previous slide, we are given percentage. Now we are given fractions, but it doesn't matter, right? Because we know that as we work them out, the total units, okay, total is 5 units. So it's the same as doing in terms of percentage as well. Okay, so how do I calculate this question? It's the same. AR, okay, of rhenium, which is Re, okay, is, let's take the first isotope, 185, okay, 0.0, multiplied by the first 2/5, right? Because it takes up 2 units of the total of 5 units. Okay, this is the first one. The second one is, second isotope is 187, 187.0 times, takes up 3 units, 3 out of 5. Okay, do the calculator, and using calculator, you will get this number of 186.2. Okay, it has no units because it's just a ratio, and it tallies with what we have here. Okay, let me show it to you. This guy. Okay, you can see that it's 186.2. Okay, and that's the answer. It tallies well. Then you may ask me, oh, then why do I have to go through this when I can just refer to the periodic table, right, to get my answer? Because the answer is sometimes, okay, they can give you an unknown element, okay, and ask you, for example, they calculate the relative atomic mass of, say, X, okay, given that the two isotopes are 185X and 187X, okay, then you don't know what is happening, right, because you won't know what is actually referring to. So you have to work this way out to find out, oh, it's actually rhenium, for example. Okay, and this is one example of questions they may ask you. But the periodic table always serves as a good, like an indicator to see whether we are on the right track. Okay, especially if they give us the name of the element already. This is more like a final recap. Okay, we in the previous two questions we talked about the relative atomic mass of element, right? Now we want to do a recap to calculate the relative molecular mass, because this is more important in our mole calculation later, okay, and stoichiometry calculations. So NaCl, how to calculate the relative molecular mass of NaCl? Okay, recall that relative molecular mass is Mr and no longer Ar, because Ar is for elements, Mr is for molecules, okay, which are all these, okay, molecules and like compounds. Okay, so for NaCl, Mr of NaCl, okay, you can just refer to the periodic table and you can see that it's actually just, okay, 23.0 plus Cl is 35.5, right? We even calculated this in the first question, and to give us 58.5 without any units. Okay, so for those who are a bit lost, 23.0 is for Na, whereas 35.5 is for Cl. Okay, so you just add them up, you get 58.5. Because if you recall, we have mentioned that Mr is sum of Ar, correct? We want the Ar of Na, we want the Na of Cl. Sorry, we want the Ar of Cl. When we add them up, we get a Mr of NaCl. Okay, this is what it means. Next one, we have SO4 2-. This is sulfate ion. Okay, so if you are scared of this minus charge, okay, let me tell you that you don't have to be, because minus charge does not play a part in molecular mass calculation. Okay, so you just work the same way as ignoring this charge altogether. So Mr of SO4 2- is the same, okay, is equals to, okay, 32.1 plus 16.0 times 4. Okay, let me explain that. Okay, you will get the answer is 96.1. Okay, so as with this, S, okay, sulfur is 32.1 in the periodic table. O is oxygen, okay, is 16. But there's 4 of them here. Okay, so I have to let me use a different color. Okay, there's 4 of them here, so I have to multiply by 4. Okay, and it will give me a number of 96.1. Okay, and so this will be all for a recap on relative atomic mass and relative molecular mass. Hopefully it helps you.